Hello. Thank you for being here with us so early. Um, some introduction. Uh, I'm George. He's Chris. Um, Joining today for a co-presentation on chaotic systems. This is the background. What changed this year? I'm a student at Aldo University. I have presented before fractional FM, and I'm also working on some machine learning applications. The patent is pending, but hopefully we'll have something soon. What we will be talking about today? What are some chaotic systems that appear in other applications, other products from other companies? We're going to go through some theory of chaos, but we're going to keep it light, so not too much math. It's supposed to be a fun, casual talk. Believe me, you can get very heavy with this stuff, and I have the resources included if you choose to do that. We're going to mention some key concepts of chaotic systems. We're going to show some code that you can use to quantify how chaotic your system is and measure some properties that you might want or not want in your system as you are designing it. Then we're going to explore some ways that we can rein in the chaos, because we might not want too much movement for our applications, especially for audio if we're sending it out directly or as a control signal. And we're going to have some interactive demos with audio. And at the end, we're going to present some final ideas and future thoughts. Okay. One company that I found is called Nonlinear Circuits. They make circuits that are nonlinear in nature. Some example modules that they have, unfortunately, they're only available in DIY form if you order them directly, but there are third-party builders. So there is, for example, a sample and hold module that instead of sampling noise, it takes a chaotic orbit and it samples that. There is a sequencer that combines noise with chaotic trajectories and switches between the two. The nice part about this company is that the designs are open source. So you have the schematics, you can look at them, you can change them, you can see how it works, and if you want some different application, you can transform it. There are also other analog favorites showing up. So there is some modules have slew rate limiting, others have light dependent resistors, others rely on phase lock loops. These are classical analog circuits. They are often based on papers, and you can find links on the website. And there is even a module simulating the brain cell of a squid, which I find most interesting. The spiking neurons. I think Discord on. Sorry. I'm going to turn off the audio for now. So another example is this company called Newfangled Audio. They are a spin-off of Eventide. They make a synthesizer called Generate, and it has 8 chaotic sources and a free version that only has one of them called Pendulate. So what they did for this, as far as I understand, is that the sources are all based on a double pendulum system, but the parameters are different for each source. So they chose some parameters that sound good and have them as oscillators in their synthesizer. What I like about this is that they added their own spin to it. They have the parameters as modulation targets, and they also have some constraints. And I found an interview that it took 3 or 4 years to make it sound musical. So they were exploring the chaotic system, changing the parameters, trying things out, until eventually they got to something that musicians could use. So, yeah. As an example of a constraint they used, if you have a pendulum with a rod of length 1, then and you put a mass at the end, the mass is always going to be in the unit circle. So we realize how that might have some good properties for defining an oscillator. And we will revisit this idea of constraining our chaotic system later in the talk. And another thing I like is that they combined it with what they figured out sounded good, which is West Coast Don Buchla style modules. So there is a wave folder and a low pass gate. So I guess the key takeaway here is that don't be limited to just chaos. You can try to combine it with other ideas if you have them. Yeah. So here we're going to look at an example of analog computing. This is the Lorenz attractor. You can see the equations up there, and it's implemented directly in circuit form. So we have the integrators, the differentiator in red that implements the derivative directly as shown in the equations up top. And the resistors at the input determine the mixing coefficients because they're added to make the derivative. And the parameters, in this case, they're constant folded into the resistor values, but in a simulation, you can change them. Yeah, and we should know that this is an inverting op-amp, so we should, our values should account for that. The capacitors in this system determine the time scale. So the system as a whole can be slower or faster by changing the values of the capacitors. And this is the phase space plot that this circuit makes. So back to the nonlinear circuits, another thing that I found interesting is that they have some very, very, very slow modules. For example, you can see that it can be built to run at different speeds by changing the capacitors, and since they're DIY, you can put your own values in there. Another module description says that it can take up to an hour for the change to appear. And there is an extreme one that can take 8 to 20 hours to complete its orbit. So if you want a sequence that is non-repeating, at least at the time scale we are interested in, some long drones or modulation that always creates something new, this is one idea. So this is a way to design a style of non-repeating LFO. Now we're going to go through some light theory about chaotic systems. So we have attractors that are invariants in the state space. The starting condition of the system will tend to go towards the attractors, and initial conditions in the attractor will stay in the attractor. We also have basins of attraction, and if the initial conditions are near the attractor, so if they're in the basin, they will tend to fall in. And the systems can be either conservative or dissipative, depending on whether the energy is conserved. And there are also fixed points that can be either stable or unstable. So in this case, we see that this system has 3 fixed points. It's defined in 1 dimension, and the black points are stable, meaning that if you move slightly away from the fixed point, you will tend to go towards it. And the unstable fixed point means that if you move slightly away from it, you will fall out. Another key concept in chaotic systems is bifurcation. So a bifurcation is when a significant change happens to the way the system behaves, and that is a qualitative change. So the entire system changes all at once. The bifurcation points can be where the system loses its stability or a new periodic orbit is born. And we can also plot the bifurcation diagram over our parameter space. So here we have 2 parameters plotted against each other. And the bifurcation diagram tells us the location and the number of the fixed points as we change the parameters. So in this example, we see that there are stable, unstable pairs, and they are being created or annihilated as we change the parameters. And we see that in this case, we have created a hysteresis style effect, so that the quality of the system changes depending on whether we are changing the parameter up or down. Another key concept of chaotic system, and there are many more of them in the resources, I'm just covering the main ones, is synchronization. So the easiest example is when we have a driven passive oscillator, and that can be, for example, RLC circuit, resistor, capacitor, inductor, and that needs an external forcing. We can also have periodical driven self-sustained oscillators. So when the driving frequency is near the natural frequency of the system, again, that's an internal property of the system, we have periodic motion. But if we change the driving motion too much, the frequency of the driving motion, then we will get bifurcations. And we also might get periodic or quasi-periodic solutions. So we can also couple two phase oscillators together, and an interesting effect is what happens when we couple together two chaotic oscillators. So you would expect that a chaotic orbit that might be deterministic yet unpredictable, you would expect that a system that is chaotic, when you connect it either with mechanical coupling or electrical, or in any case, with another system that is chaotic, the natural thing to expect is even more chaos, right? But as it so happens, in some cases, we have two chaotic systems that, when they're connected together, we have a perfectly periodic motion appear. So that's one effect that can happen. And in this example, we see how, well, we're plotting the time series in the first, in the left, and the phase space on the right. And we see that when we couple two systems and they're apart, there's chaos, but then with a different set of parameters, we can have some notion of periodicity, and in the end, we have some fully periodic motion for a different set of parameters. So what are some ways we can quantify how our chaotic system behaves? So some mathematical tools to describe it. If we have an n-dimensional system, we can use n-1 dimensions to define a Poincaré. I'm not pronouncing that right anyway. Surface. And we are counting how many times does a trajectory of the system cross the surface. And we are only counting one-way crossings. So if it goes in other direction, we don't count it. So the points that appear, oh, that's just some slide. The points that appear in the hyperplane that is defined this surface, they are the Poincaré map, and they are implemented in the Julia library dynamical systems as these functions. Another way to quantify the chaotic system is with Lyapunov exponents. So the idea here is to evolve the system in time, forward or even backward, doesn't matter. According to, well, it does matter, it's going to be different, but you get it. According to the dynamics as they are linearized in a point. So we can imagine that we have a starting point, x, and we have a k-dimensional volume expanding outwards from it. And we want to measure how does this volume increase or decrease along its dimension. So is that going to work? Well, not really, because we are going to accumulate floating point. We have a finite floating point precision, which means that eventually, as we evolve the system for a long time, it's going to lead to overflow or underflow. And another issue is that usually what happens is that one dimension will be the scale of expansion or contraction along its dimension is exponentially different. So as we evolve them in time, one expanding direction will dominate the system, and it will be, you can think of it as almost a vector pointing it in that direction. And that can ruin our measurement. So the solution is to take many small steps, each with a delta taf, and we normalize, we make the volume orthonormal again after each step, and we can accumulate like that. And the interesting part about the Lyapunov exponents is that they are a description of the system that is almost invariant to the starting point. So we can pick another point in the state space, and we will likely get the same Lyapunov exponents. This is in contrast with standard deviation or mean measurements. So the Lyapunov exponents are, in a sense, a better description of the chaotic system. And here we see example code from the Thatcher's book. The code is in Julia. You don't need to know all this. You can just call the function. But this is how what we described previously with the volumes and the dimensions works. Another way we can quantify our system is using delay coordinates embedding. So what is that? What if we only have measurements, for example, from a circuit, an oscilloscope, one channel, and we don't have, obviously, the entire state space. We only have one time series. Can that be used to describe the system? Intuitively, you might think that probably it's not enough, right? It's just one sample trajectory. It might have many. The system will be more complicated than that, surely. But there is this idea where we delay the time series, and then we stack it with future or past copies of itself. And we can create more dimensions in this way, but they're not true dimensions of the system, but they are still a good description of the system. Now, since the attractors don't change over time, the delay coordinates will be able to reveal some deeper truths about our system. And usually the choice of the dimension and the delay time isn't that important. It will work as long as we choose a large enough dimension. And this is the function we can use from the library to create a delay embedding. Yeah, so this is some principles about controlling a chaotic system. So usually when we have something that is too chaotic, it might sound like noise, even though it is not, it is deterministic. So when we are making a musical application, we will want to constrain it, in a sense, like the newfangled audio synthesizer. So generally, we might want to define some invariants that we want the system to have, and then we enforce them, or if the system doesn't respect the invariants, we can change it so that it does. This is a design principle. Again, we are musicians, we can do anything. But it might take some time to discover a good design space. So we can resort to stacking the odds in our favor. We can explore the system using those tools and other interactive sessions that I showed you. And we can find an interesting region in the parameter space, and that is what we're going to expose to the user. So they're not going to get the entire system. We're going to map the controls of our synthesizer or module to interesting parameters. So what might be some interesting effects in the system? Bifurcations are always a great choice because they change the quality of the system, and it might be sudden. We might want to have an interchange of longer or shorter time scales. So some calm sections where nothing happens or almost nothing, and then some sudden movement. Chaotic systems are usually good at generating that. And of course, we can have quasi-periodicity, which is when the frequencies of the the periodic components are not rational, they're not multiples of each other, basically. So we'll get motion that is, in a sense, regular, but it's also not exact circular, for example. And we can, of course, constrain or map the user controls so that they respect our design principles. And this, in a way, it's similar to choosing a low modulation index in FM synthesis because we want the results to be musical. And now I will pass over to Chris, who will introduce you some example coding systems.
Hey guys, I hope talk's been going well so far. I think what George has said is very good overview in general of the chaotic systems, right? And sort of it's not so much directly applicable to some systems that we can imagine, like a musical system or like a compositional system. And I think what I'm trying to go and attempt to do here is sort of bring it back down to somewhere we can take a safe entry point in. And I'll give you some examples of basic chaotic systems that we will be able to implement, maybe directly in our real-time environment or in a simple Python environment, and be able to sort of sonify the outcomes of the behavior of the system, right? So I think the first case, and I think more importantly, is to hold on to some safeties that you have along the way. So it might be a bit scary, but I want to just say that time is at least always linear. So we don't experience nonlinear time in any of these, although you can implement that if you want. And thank you, that's a good joke.
It's going to be the best quote of the
almost always linear, right? And in the case of the double pendulum, we have an input to the, sorry, I keep turning around, but I should just be pointing with my hands. We have an input to the first pendulum that's connected to the rigid surface. It's at least some sort of linear motion, right? It's harmonic motion. But in a lot of cases, you can actually input stuff that might not be a linear input. So for example, in the case of a distortion pedal going into a film capacitor, the film capacitor, the old kind with the plates curled up, so that exhibits some sort of harmonic motion as well, right? But your signal going into that is not a linear signal anymore. So what happens? You get even more chaos. So what really I'm trying to say is, and I'm going to reiterate this point again that I said last year, is the universe is the best computer, right? You put in the most nonlinear stuff to another nonlinear system, and you get perfectly fine real-time computing. Yeah. So let's begin. I made some gradient examples along the way, and I hope to be able to inspire you to make your own chaotic system at the end of the day. Right, so starting with the double pendulum, we have this system that is attached to a fixed point at the top. We have some length. We have a point there. It might not be a mass. It can be a mass, but you can imagine it as a point. And then we have another length below that, which is attached to another mass below that, right? So the thing is with these systems is that they depend highly on the initial conditions of the system. And what does that mean? You could imagine, and you can try this experiment later. You can have a friend and take their tag, and you can tie your tag to another tag. And you can wave it around and see if you can get it to, predict this to get the same motion each time. And you might find points or basins of the system where, as you move it with some sort of resonance, that it will be able to retain similar form of motion, right? But most of the time, you'll get this erratic behavior, right? So the whole idea is that it's always deterministic and it's not sort of random across time. It's not like a random or like an analog random generator, I should say, right? And so it being, sorry, this tag is annoying me. Just adjust that. That being said, I think what it is that we as humans, we tend to be able to detect patterns in the long run. And if we learn the system enough, I'll say that with very, very big open inverted commas, if we learn the system enough, we'll be able to find some points that we can take and, we know that this region of behavior is what exactly we want, and we can take that and implement it in the system we want. We want to get out of like the musical system, right? So I think what we have to keep in mind is that because of the nonlinear dynamics, and we've been talking about that for a while, the response to these initial conditions, like the setup of the system, will cause the resulting behavior of the system to be very unpredictable. And I hope to show you that in an example. Can I just go alternate? Can I just command tab out of this? Is that okay?
Just go there.
How do I go to the browser tab?
This. Or, just this.
There we go. Okay.
Thank
Thank
fingers,
you.
Yeah.
All right, so we've set up a simple gradio thing here, and I hope you can demonstrate. So I've set up some default parameters, and you can see that these are corresponding to the lengths of the pendulum and the mass, and we have some durations. And what I'm going to do is I'm going to modulate sine waves frequency with the positions of the pendulums. So let me do that. There we go, and I should get you a plot. So you can see we plot the angle of both of the pendulums against time in this case. And again, time is linear, so shouldn't milk that anymore. All right, so let me hear it. Oh yeah, I'm mute, sorry. Give me a second. I'll bring it down first so they don't kill everyone. I'll try it again. Right, so you get really quite a very simple modulation of a sine wave, and you didn't really have to think too hard about how to really squeeze the interesting behavior out of it. So as we go on, you can change the length of each pendulum, and you can see just by changing the lengths of the pendulum, you get very different plots. And there we go, right? And if I just change maybe the mass of one of them, I might get maybe not so different this time. That's not so different, right? But you can see that if I just, increase something like this, yeah, you get quite wildly different stuff, and how this corresponds to the actual sonification. Right? So you get interesting behavior out of this. Okay, go back to that. And we will share the link or something afterwards, and on the Discord channel, and so you can all play with the system at your own time. Oops, sorry. Present. How do I go back to play? Is it okay? Thank you. All right, this is the image of the plot and audio demo. All right, and just now George talked about the Lorenz attractors, and the Lorenz system is part of this chaotic systems or system with non-linear dynamics. And it, I guess some background is that it was used to sort of model atmospheric behavior. And you can see that there are these butterfly pattern, known as, and I guess that's where the term the butterfly effect comes from. And there's this household saying that if a butterfly flaps its wings in country A, tornado happens in country B. I think it comes from this because it demonstrates how very seemingly normal initial conditions tend to result in very unpredictable behavior across time, right? And similar to double pendulums, I hope to demonstrate this to you with an example. And just some other small details about the system. We have these convection rates in 3 dimensions, and we have Rayleigh number and the Prudent number. I always pronounce it that way, but I don't know how to pronounce it. So maybe the keen among you can let me know later. All right, so let me just go to that. Escape first. Oh, sorry. And we have a tab here. And so this is the plot of the Lorenz attractor. And I won't attempt to plot it again because it takes a while to simulate the stuff. But yes, I'll let you hear it. So what we're doing here is we have 3 different distortions that are stacked up one after the other in series. And what we're doing is we're modulating the levels of these distortions with the x, y, z coordinates of the Lorenz attractor system. And what you get is this really quite cool, almost tremolo kind of sound. Being the guitar pedal review watcher, I'm going to play you the clean sound. You get the idea, right? So what you get is this really cool, non-periodic tremolo type sound with distortion. I think it's really nice to be able to take all these very well-studied systems, and there's a whole bunch of them. You can go visit a zoo almost, and take them and implement them into your musical effects and be able to get interesting results out of them without having to do sort of much exploration in terms of the heavy math. I think you just need to learn it and take the already well-defined equations and then plug it in. Yeah. So, sorry, wrong way. This is the gist of it. I'll let you watch that for a bit. Here we go. Yeah, you get the idea. Okay. So the last system I want to show you guys is the Gkountouras circuit. And the Gkountouras circuit is one of these systems that's sort of, I know it as the system where you start to be able to imagine your own parameters of a physical system that might not be necessarily physically possible. So here we have this system is, but you can see as you go down the road, sometimes these systems don't tend to behave like that. And with this, you can see this special component on the schematic diagram over there. And what that is nonlinear negative resistance, which is just some function. And it's called a Gkountouras diode, but you have this implementation of it. And when you start to play with it more and you realize all these, it sets it up so that as you change some parameters here and there, the system kind of goes crazy as well. So as being the math person I am, I'll leave the implementation of this as an exercise to the reader. But yeah, I think overall we have these sort of systems where we are able to put in some initial conditions, which are maybe some simple numbers, and we get this very nice, unpredictable behavior out of them, and they don't necessarily, they're not too far attached from reality. You can still kind of imagine some systems, but some of them might be, so just fair warning. And I think I would like to invite George back, and we can all start to wrap up. I think we want to have some questions as well. And so, yeah, George, could you please join me up here, and we can talk about all the stuff.
Okay, let's thank Chris for the beautiful demos. What are some ideas for the future? So as embedded devices grow more powerful, I don't know about you guys, but I have a daisy seed board. We will start to simulate larger real-time chaotic systems, and these aren't really heavy. These are we can evolve them forward in time. You don't need fancy solvers or anything like that. You can even write it in an afternoon, the simulation. So please do experiment. And how could I not mention my fractional derivative operator that I introduced last year? I don't know if anyone has implemented a chaotic analog circuit with it, but it could certainly be an interesting application. So instead of regular differentiators, you have fractional ones. We can also use chaotic systems as modulators, and Chris came up with this idea. We can have GPU-powered simulations if these systems are large and they don't interact too much. That is something that we need to watch out for. But we can simulate them in parallel and evolve it in time. And of course, we can incorporate different analog computing ideas like filters and slew limiters and comparators and anything that we know from that. I would briefly go through some resources because I want to leave time for questions. So this is the synthesizer. Most of the material from in this talk was adapted from the Nonlinear Dynamics book by Datcheris. What I really like about this book is that it is accompanied by high-quality open-source code. So dynamic systems are very interactive, as Chris said, and you have to dive in and experiment, try different things, and having code that does that is very helpful. And in this case, you don't even have to write it; it's waiting for you. This is the Nonlinear Circuits website. An interesting previous talk in ADC. And this is interesting. So there is a talk in another room being given right now. I found this online. I didn't know they were giving an ADC talk. I was just looking for chaotic systems, but they're simulating 550 masses that are connected with springs. Again, not all of them, but some of them because it's not tractable. But it's GPU powered, so it can do all that computation. And please watch that when it's available. I met him, great guy. Yeah, and Ian Fritz has been doing chaotic circuits for 20 years, and yeah. We used the pedal board library in some of our previous demos. I don't think we used it in the end. And this is the chaotic system. And the traditional introduction is this book. But again, I recommend that you have some code. I will go to questions if you have some online or offline.
Thanks, guys.